Title of my talk is Collective Dynamics of Liquids in Bulk and Narrow Channels. And here is a short outline of my talk. First, I will talk about the motivation of this study. We'll show the difference in macroscopic and atomic scale picture of propagation of collective excitations in disordered systems. Then I will show how we can calculate from molecular dynamics different time correlation functions and what is non-ergodicity, which can be observed in density time correlation functions. Then I will talk about theory, about a methodology for estimation of dynamic eigenmodes in liquids, and some analytical results will show. Then I will show very new results for eigenvector analysis for collective excitations across the viscoelastic transition. And finally, the last item is the dynamics of a model liquid in a narrow channel. And I will finalize my talk with conclusions. On a very primitive point of view, so the dynamics consist of vibrations and diffusivity, but it's much more complex picture. So if we can look at the specific features of dynamics in different states, for example, in liquids, in supercooled liquids, in gases, in comparison with crystals, so we have to distinguish that for regular liquids, there is always exponential decay of density time correlations. And for regular liquids, we have standard Brownian diffusion with this famous Einstein relation between the mean square displacements and long time asymptotes. If we got under the melting line, so we got in the supercooled regime. So for supercooled liquids, dynamics is absolutely different. There emerges a slow non-exponential decay of density time correlation because of dynamic heterogeneities, which the regions of solid-like and liquid-like motion of particles, they are slowly changing and moving in liquids. And diffusion is only jump-like diffusion, and this expression is not anymore valid for Brownian diffusivity. But if we quench very quickly liquid and we got to the glassy state, it's totally different. Because in glassy state, because of the arrest of particles, the diffusivity is zero. However, this is still not really equilibration of the system. It's non-equilibrium state of matter, glassy state. But in this state, because of this arrest of particles, non-ergodicity emerges. And this means that we will see on the shape in the time dependence of density time correlation that there appears a non-decaying plateau, long time plateau in the time dependence of density correlations. And in comparison with crystals, for crystals, everything is very simple because we have stable in time potential energy minima that we can expand the potential energy around this minima and work in harmonic approximation. It's easy way to estimate dynamic metrics and calculate eigenfrequencies of longitudinal and transverse phonons. And so it's a standard procedure for crystals. And the phonons, these are just waves of small displacements of particles from the position of equilibrium of the potential energy medium. But for liquids, it's absolutely different. On macroscopic scale, we have even absolutely different mechanism of sound propagation. So if we will look on the left picture on the left, so it shows like on macroscopic scale, we have a pressure wave. And the very specific feature of this pressure wave is that this compression and decompression is much faster process than the time of thermal equilibrium in the system. So that's why in compressed region, the temperature is slightly higher. And in decompressed region, the local temperature is slightly lower. That's why there is immediately a gradient of temperatures, and thermal diffusivity processes started. So I would like to remind thermal diffusivity, this is diffusivity of local temperature. And namely, this diffusivity of local temperature is manifested as a central peak in dynamic structure factor. So dynamic structure factor is basically main quantity of interest for experimentalists, because they can directly measure dynamic structure factor in neutron scattering, in elastic neutron scattering experiments, or in elastic X-ray scattering experiments, and typically for very small wave numbers, because the dynamic structure factor is a function of wave numbers and frequency. So the scattered intensity of X-rays or scattered intensity of neutrons, they have typical three peak shape. So the central peak for very low wave numbers correspond to these thermal fluctuations, to processes, relaxation processes of temperature. And two side peaks, called as brilliant peaks, correspond to acoustic excitations. And what experimentalists usually do, they look at different wave numbers for the positions of these side peaks, and in this way they obtain this sound dispersion frequency versus wave number. So this is how the experimentalists analyze the dynamic structure factor. For theorists and people working with computer simulations, the good thing is that dynamic structure factor is just time Fourier transform of density time correlation function. Here f and n as a function of wave number and time is the density time correlation function, and time Fourier transform allows one to calculate dynamic structure factor and compare with a real experiment. However, this is macroscopic picture. I would like to remind you that macroscopic picture means that this is kind of continuum limit. However, if we want to work on atomic scale resolution, it's obviously that many other processes connected with scattering of atoms, different atomic correlations, etc., they will contribute to these dynamic processes. That's why we distinguish between so-called hydrodynamic modes and non-hydrodynamic modes. Hydrodynamic modes are those which exist on macroscopic scales, and typical for them is here, for example, if the time correlation in liquids decay exponentially, we can write in this form, and this z as a function of wave number, it represents, in general, it is a complex number. Real part corresponds to damping of this collective mode, and imaginary part corresponds to the dispersion law or frequency of this propagating mode. And if we would look at the typical feature of hydrodynamic modes, we will see that damping is proportional to wave number to the square. And It's the same for hydrodynamic relaxing modes, which are purely real numbers. So usually in this representation, propagating processes are represented as pairs of complex conjugated numbers, and relaxation modes are represented as purely numbers, which are for hydrodynamic modes, they are proportional to wave number to the square. And this is direct relation to the conservation laws. For example, we have conservation of energy, we have this thermal diffusivity, we have conservation of momentum, we have viscous relaxation. If we have in binary or many component liquids, conservation of concentration, that we have this diffusive relaxation, and so on. However, non-hydrodynamic modes are those which essentially differ from the hydrodynamic ones. You can see as this real part of this exponential, yes, when wave number goes to 0, it goes to a constant. That means that these non-hydrodynamic modes, they do not survive on macroscopic scales, because here it's a finite non-zero value. They just simply die out. They do not survive on macroscopic scales in comparison with hydrodynamic modes. And the main task of theoreticians and also people from simulations, when we calculate the density time correlation function, it's our task is how we can extract information from those non-hydrodynamic processes, because we want to explain processes on atomic scale or on nanoscales. And the examples of these non-hydrodynamic modes are like shear relaxation, structural relaxation, or optic-like excitations, or even very specific excitations which exist only on nanoscales. These are like shear waves and heat waves. And all these we can calculate directly from analysis of density time correlation functions obtained in molecular dynamics. And since this is kind of tutorial for people who didn't calculate before time-dependent properties from molecular dynamics, I would like to explain some very, very simple things. So molecular dynamics simulations are deterministic computer simulations. That means that if our algorithm is totally correct and the time steps is chosen very well, quite small, then all the conservation laws are okay. And then the very first configuration of our production run and very last configuration of the production run, they are connected by deterministic laws. That's why we can calculate time-dependent correlations. And we, since we, as the output, we have trajectories of particles, velocities of all particles along trajectories, forces which are acting on particles along trajectories, single particle energies, and all these quantities are changing from configuration to configuration. So we can calculate the time-dependent correlations of these quantities. We have to distinguish single particle time correlation functions like velocity autocorrelation functions. This is expression. Here is the correlation of velocity of the ith particle at 0 time moment, and then with its velocity. This is a scalar product of two velocities, initial velocity and the velocity at time t. And it is averaged over ensemble of particles of the same kind and also of the over the time origins. I will explain in the next slide what it means time origins. And we also can calculate different collective time correlation functions like density, density, current, current, energy, energy, and so etc. Especially important are time-dependent correlations which probe different spatial scales. So in this sense, we can calculate one-hole correlation functions which are calculated in real space, or we can calculate so-called intermediate scattering functions which probe the correlations in momentum space. So, and is a prime interest for us are the density time correlation functions. The definition is shown here. And I will show what is density expression for density. And this is for time correlation function current, for longitudinal and for transverse currents. So, and another important thing that in computer simulations, we simulate a finite system which is under the periodic boundary conditions. That's why we cannot take deliberate wave numbers. Our wave vectors must be compatible with periodic boundary conditions. So this is how we choose the wave vectors from our simulations, and L is the length of the molecular dynamic box. So this means that if we want a very small step in wave numbers, we have to simulate very, very large systems. Okay, so we know what we have as wave vectors. Now, we can sample from our trajectories space Fourier components of particle density. It's very easy. We have to know just the positions of particle and moment t. And this is scalar product wave vector and the position of particle. And in very similar way, we can calculate longitudinal component of current, of total current, and transverse component, which is two-component vector in the plane perpendicular to the direction of vector k. Because here is a scalar product, wave number and velocity, and here is vector product of wave vector and velocity. So in this example, you see that the dynamical variables of density we can calculate easily, having information just about the trajectories, and to calculate these dynamical variables of longitudinal and transverse currents, we have to know the velocities of all particles along the trajectories and their positions. That's it. It's very easy. And then we simply have to select the length of our time correlation functions of interest. Like, let's say n sub f is 3,000 configurations or 10,000 configurations. Suppose we have stored 100,000 configurations, and then we calculate this, fixing this is the initial configuration, and calculate for each configuration of the length of time correlation for each from I equal from going from 1 to n sub f. We calculate this product of real parts and imaginary parts. And then we shift the origin of time correlation function by m configurations and repeat again the same. In the end, we have ensemble of those collective time correlation functions with different origins. And simply in the end, we simply average over this ensemble. In this way, we obtain the average, as I showed in the previous slide, this averaged over origins, over the ensemble of these different origins, we have time correlation functions. And look what we have from molecular dynamics. Let's say for liquids we have this shape of density time correlation functions. The exponential decay and oscillations are due to propagation of these collective modes with selected wave number. And what is important, as I told you before, that there is exponential decay of this correlation. For in regular liquids, these correlations always decay to zero. And the initial value of this density time correlation function is the static structure factor. For glasses is absolutely different. As I told you before, that if we quench very quickly the liquid system, so we get the arrest of particles and non-decaying correlations. And you see here non-decaying plateau. It is not decaying to zero. It is unstable, and this is so-called idealized glass transition. Namely, the glass transition temperature is defined by temperature when this non-decaying plateau appears. So non-ergodicity when appears. And f of k, this value of this plateau in density correlation, is called non-ergodicity parameter. So in comparison with liquids, we have that again the initial value of density time correlation functions is static structure factor S of k, and in the limit of very large times, we have this non-decaying value f of k, which is non-ergodicity parameter. How important is non-ergodicity for our understanding of propagation of different excitations like sound? Okay. Maybe I will talk a little more about the confined system. For example, a very simple model system to study porous media is so-called disorder matrix. Disorder matrix means that we have put in our box some areas which are impenetrable for liquid particles. So they are moving in the restricted space between those motionless, impenetrable obstacles. And in this way, we can model different kinds of porous media. So on the left, you can see the different porous media. And what is interesting, that in 2007, Vincent Krakowiak, who is a disciple of famous Jean-Pierre Ansen, he showed that for those systems like liquids in porous media, depending on density, there emerges exactly the same non-ergodicity like in glasses. And you see here, depending on density, these are normalized density time correlation functions. Here is decay to zero at some point, at some density. They are non-decaying plateaus, so non-ergodicity emerges in fluids in porous media. So this means that dynamics of liquids in porous media is very, very different from dynamics of liquids in bulk. And how important is the non-ergodicity for propagation of acoustic excitations? Like for regular liquids, there is a standard definition of the adiabatic speed of sound, how the sound propagates on macroscopic scales. And Well, it can be calculated from molecular dynamic simulations, either using thermodynamic relations or using some wave number dependent quantities, like here on the right is shown. Like we can calculate the wave number, this limit when wave number goes to 0, and this is a smooth function where gamma of k is k dependent ratio of specific heats, and this is structure factor, and this function is very, very smoothly smooth function of wave number, and this is thermal velocity standard constant Boltzmann times temperature divided by m and square root of that. This is the standard thermal velocity. So, and there is no macroscopic transfer sound for liquids. For glasses, it's namely where the non-ergodicity can emerge. Intuitively, on macroscopic scales, it should be propagation speed should be the same as in elastic medium. And it is written here, expressed through the instantaneous bulk and shear moduli. However, in 2000, independently, two groups, one by famous Wolfgang Goetze. Wolfgang Goetze is a person who proposed the mode coupling theory. He's a famous theoretician. And independently from Goetze, Giancarlo Ruocco in 2000, again, two different papers. One appeared in Physrev E, second in Physrev Letters. They suggested that the macroscopic speed of sound for glassy systems must depend on the non-ergodicity parameter. And this expression, it's right now, it's a discussion in the literature. What is the macroscopic speed of sound for glasses? And as you saw before at the previous slide, that porous media in some sense also remind us about the properties of glasses. So non-ergodicity is very, very important for propagation of this. Let's go back to the liquids, to the bulk liquids, and to the issue how the non-hydrodynamic modes can contribute to the dynamics. Okay, so we already know everything about the propagation of hydrodynamic modes on macroscopic scales. But outside, and when we perform molecular dynamic simulations, because we have quite a small system of particles, we usually work outside the hydrodynamic range. That's why it's interesting to look what happened to dispersion of sound modes. And people started from the very beginning of computer simulations, and they saw, observed that the standard, this what we call apparent speed of sound, when we divide the dispersion law by wave number, we have this value which is in the long wavelength limit correspond to adiabatic speed of sound, but we see this increase. So the red plus symbols corresponds to the apparent speed of sound outside the hydrodynamic range. And the question was, it was observed for almost all dense liquids, and it was called so-called positive sound dispersion. And the theory of positive sound dispersion, first Ernst and Dorfman in 1975, they tried to explain the positive sound dispersion by so-called non-analytic corrections to the hydrodynamic dispersion law, which emerges due to mode coupling effects. And you see that indeed, if we will put it here, we will have some deviation from the standard hydrodynamic dispersion law and from standard decay of correlation. However, when people started using this expression, they found later that this coefficient alpha, they didn't have correct dependence when we calculated at different pressures and density. So, and people decided that perhaps this expression is not really correct for first correction to the hydrodynamic dispersion law. Then in 2000, Balukhani and Skupinio with co-authors, they proposed within the memory function approach, they were playing with channels, with different channels in the second order memory function, and they were able to show the emergence of positive sound dispersion in some cases. In 2010, our group from Lviv, we showed theoretically and confirmed by molecular dynamics simulations that first correction to hydrodynamic law within the thermoviscoelastic model is proportional to wave number to the cube. And this coefficient beta was either positive for dense liquids or was negative for very rarefied fluids. And it's typical, for example, for hard sphere fluids, we really have a negative dispersion, not positive, but negative. So we were able to explain by our theory the emergence of positive sound dispersion because of, I will show a little bit later, but because of interaction with non-hydrodynamic shear stress relaxation. Also in 2016, Russian group proposed a very simplified approach. They were simply removing the high frequency bulk modulus and substituted instead of it macroscopic adiabatic bulk modulus. That was totally incorrect. It cannot be justified in any case. So it's totally wrong theory. And let's now go to the our theoretical approach, how we can explain the contribution from non-hydrodynamic processes in liquids. So, and this is what kind of different approaches are. So we need to obtain some analytical expression for density time correlation function. Of course, in hydrodynamics, this is macroscopic approach. For continuum, this works only in wave number goes to zero limit. Then to go outside the hydrodynamics, people were using generalized Langevin equation, and in Laplace transformed form, it results in very easy, simple expression where m as a function of k and z, so this is so-called memory function, Laplace transform memory function. In its turn, this memory function is itself a time correlation function. And that's why for it, we again can write the same expression, having the initial value of memory function of first order. And then continuing this, we can obtain a very long chain of memory function, like lowest memory functions and memory function of first order, memory function of second order, and at some level we have to cut this chain of memory function and then obtain some analytical expression for the density time correlation function. Our approach is different in that sense that this memory function approach is solely for a single density correlation. However, in hydrodynamics, you are in fact having, for example, for simple liquids, you have three conserved quantities: number of particles, total momentum, and total energy. So there are 3 balance equations. So in fact, we would have to perform similar simultaneously expressions for density time correlation, the current time correlation function, energy time correlation function. And this can be done in matrix formulations of generalized Langevin equation. So that was the main how people solved the system of hydrodynamic equations. Exactly this is the form, because generalized Langevin equation for Laplace transform functions, it has very simple form, where this matrix T of K and Z is called generalized hydrodynamic matrix. So in this sense, using density, current, and energy, we can construct this hydrodynamic matrix T of K and Z and solve it analytically and obtain exactly what is known from hydrodynamic theory. And now is the idea, okay, can we extend this approach to take into account non-hydrodynamic processes? Yes, we can, because we can construct some dynamic variables which would be orthogonal. Orthogonal means that the cross correlations between equal 0. Orthogonal to density variable, to current variable, to energy variable. So we really can do. And in that sense, we are increasing the number of equations, the size of this eigenvalue problem for this matrix T of Kz, and we know exactly how to calculate this using our molecular dynamics. For example, we can easily sample, as I showed you before, density of particles, Fourier components of total currents, Fourier components of energy. And also we can calculate, for example, first time derivative of currents. If current is proportional to velocities of particles, then the first time derivative of velocities contain information about the microscopic forces in our system. So this is totally quantities which are not even considered in hydrodynamics. There is no information about microscopic forces. But in our approach, we exactly combine the macroscopic picture, like hydrodynamic equations, and we add additional equations which contain information, for example, from microscopic forces on atoms in our systems. Or the first time derivative of energy. This means the energy current in our systems. This is also non-hydrodynamic variable. In this sense, we can calculate n by n in general, generalized hydrodynamic matrix, and we have the recipe for this matrix. This is matrix of time correlation functions and matrix of Laplace transform time correlation functions. It's easily to calculate them from molecular dynamics. And then eigenvalues can be either real, as I told you before, and correspond to relaxation processes, or pairs of complex conjugated numbers. And these corresponds to propagating excitations. And since this is the size of this eigenvalue problem is much larger than the hydrodynamic one, we can obtain both hydrodynamic modes, non-hydrodynamic modes, and have their contributions to the dynamic structure factors. And look how this works if we compare this, for example, time correlation function, density time correlation functions, and our theoretical approach, which is called generalized collective modes approach. How they recover, how theory recovers the density time correlation from simulations and current time correlations from simulations. Here is some analytical example, some very simple analytical model. When we, let's forget for now about the temperature fluctuations. Let's suppose that the temperature in our system everywhere is the same, and we have two dynamic variables. So density is hydrodynamic one, and longitudinal current, another hydrodynamic one, and we extend this set of dynamic variables by non-hydrodynamic one, which is first time derivative of the current. And it is proportional to, it contains information about the microscopic forces in the system. And it appears that we, in the long wavelength limit, we can analytically obtain this matrix, generalized hydrodynamic matrix, and we easily can see that separate this part, which has a block structure, and this part. And this second part, we can treat as a perturbation. And for this non-perturbed part, we immediately can see what are the eigenvalues. Eigenvalues are propagating, non-damped propagating modes with isothermal speed of sound, because there are no temperature fluctuations. Okay, and the eigenvectors have this form for two sound modes, and also non-perturbed stress relaxation mode. And again, we have analytical expression for it, and again have how this eigenvector looks like for this unperturbed systems. It's very easy. And then when we solve the whole problem, we obtain two in the end. We obtain two propagating eigenvalues already due to coupling in this, due to this second matrix. Yes, because coupling is here. We obtain that there appears damping because of coupling with stress relaxation mode, and appears a first correction to the hydrodynamic dispersion law, which actually is a positive correction, this positive dispersion. And this stress relaxation mode has this expression, and it was many times confirmed from molecular dynamics. Now, we can now look at how behave the eigenvectors as functions of wave numbers. Okay, so for component for the sound eigenmode, so we want to look at the origin of sound on macroscopic scale, and then how this origin of sound excitation changes when we increase wave numbers. And we can analytically obtain these absolute values of components of eigenvectors and compare with our molecular dynamic simulations here. So here in this, for very, very small wave numbers, we have this correspondence, exact correspondence to these analytical results. But then outside this hydrodynamic range, we have very, very clear picture how the origin of sound changes with increasing of wave numbers. So in this region, in hydrodynamic range, we have sound solely composed of density fluctuations and current fluctuations, so totally of fluctuations of conserved quantity. So this is hydrodynamic mechanism of sound propagation in liquids on macroscopic scales due to local conservation laws. But then contribution from microscopic forces increases and becomes dominant. And this is here in this region is almost purely elastic regime of elastic mechanism of propagation of short wavelength acoustic excitation, exactly like in solids. So this is a transition from one macroscopic mechanism of sound propagation in liquids to the atomic scale mechanism, which is elastic like in solids. And here is we can look at the when we increase and take into account fluctuations of temperature and extend this dynamic variable to the heat current, and so take much more complicated, sophisticated problem, and we obtain the same picture that after 0.5 inverse angstroms, this is just the maximum of this positive dispersion. So means that this is a crossover when the contribution from microscopic forces becomes dominant, and elastic mechanism for larger wave numbers becomes dominant for liquids. And also here is how we I have 10 minutes. Okay, I will speed up. This is how all this and how we can confirm that this is elastic mechanism, because we can perform MD simulations for crystals, for let's say argon crystals, calculate longitudinal and transverse current time correlations, find numerically frequencies of these propagating modes, and calculate analytically from exactly taking current and first time derivative of current, and we can recover exactly. This means that we take into account only elastic mechanism for crystals, and it works perfectly well. So there is no information about some harmonic approximation, about some energy minima. No, we directly from this theory, we have this expression, and if you calculate it in molecular dynamics, this static correlation functions, you immediately have the dispersion of phonons even in crystals. So this is how this theory works for liquids and for crystals. For crystals is pure elastic mechanism of acoustic excitations, while in liquids we have a transition from macroscopic hydrodynamic mechanism of sound propagation due to conservation laws to change and this viscoelastic transition to the elastic mechanism of short wavelength acoustic excitations. Okay, I have 7 minutes, perhaps 10 minutes, 7. Okay, now what about fluids very confined in very narrow channel? It's another very interesting problem, which we studied together with Adrian Huerta from Mexico and Victor Perhamenshik, who was at the Institute of Physics. Now it's he is 5 years working in the Center of Theoretical Physics in Warsaw, and Andriy Trokhimchuk from my institute. So, and we performed, Victor Perhamenshik was able to analytically obtain exact expression for partition function for such a simple system. This is a quasi one-dimensional system of hard disks, but it's very interesting because depending on density, you see here density, when all the particles have this hard disk along the channels are touching each other, this density is equal to 1. However, if the channel width is less than 2 diameters, but larger than 1 diameter, we have even larger than 1 density, linear density in this system. And you can see on this picture that we have for large densities, the profile in y direction shows that here forms this kind of zigzag structure. It cannot be exactly crystal zigzag, but it has some kind of defects shown here in the middle, some defects. But this is extremely interesting system for study because it allows analytical solution and also computer simulations. We simulated these quasi one-dimensional fluids in these narrow channels and obtained very, very interesting dynamic properties. For example, here is a standard velocity autocorrelation function because we can decompose velocity autocorrelations along the channel and in transverse direction. And especially in transverse direction, we see here very, very qualitative difference with the density of this fluid. And also we observed very similar in collective dynamics because here, if the linear density is shown here, a linear density for this quasi one-dimensional fluid is quite small, it's 0.5. We have kind of dispersion of longitudinal modes in gas system, in real gas system. And in transverse direction, it shows just the beating and reflecting from the walls in y direction. But then, when we increase the density of such system, we have a transformation, both the longitudinal dispersion and transverse dispersion. We have emergence kind of brilliant zones here. You see how this sound dispersion goes again to zero. It's kind of crystal, but crystal with defects, but it's really something new. Nobody before did this calculation. That's why I wanted to show you, because these channels very often show how the confinement, how the geometry of this confinement drastically affects the collective dynamics of liquids. And I will finish my talk with some conclusions. So we were able to develop a general methodology to calculate dispersion of collective excitation in melts, glasses, and crystals, which is based on a combination of molecular dynamic computer simulation and generalized Langevin equation. We were able to see the role of non-hydrodynamics modes in collective dynamics. And actually, the future of this direction of liquid theory is in decoding of the shape of density time correlation to understand the contribution from non-hydrodynamic modes, from these which exist only on nanoscale, on atomic scale, etc. And there are lots of open issues. Nobody knows at the time what is the macroscopic limit of the speed of sound in glassy systems, how the non-ergodicity would affect this propagation speed in confined systems. And there is a challenge to propose a theory of collective dynamics for this quasi one-dimensional systems. And I would like to thank my colleagues, Giancarlo Rocco from Rome, and Igor Mryglod and Andriy Trokhimchuk from my institute for contributing to all these studies, and the National Research Foundation of Ukraine for funding. So thank you very much. And well, I guess I have a few minutes left just for questions. Okay, thank you.
Thank you for that. Very informative talk, please. Please, Sergey Puripovich.
Taras Mikhailovich, thank you very much for a very interesting lecture. And as I understand, this lectures and this description and calculations are related to the systems like glasses and liquids. And I would like to ask if what is the role of interaction potential? So we didn't mention what is the character of interaction. So if we consider some long-range interactions like in Coulomb systems, probably we could have all also something like longitudinal difference in longitudinal and transverse sound, not only in glasses but also in such systems due to the long range interactions. Maybe,
Yes.
maybe it is well known. I know.
Yes, of course, because in systems with long range interaction, in addition to the hydrodynamic equations for conserved quantities, these balance equations for conserved quantities, you additionally will have the equation for local electroneutrality condition. And it will change. That's why the spectrum of collective excitations and relaxation processes in systems with long range interaction, like in molten salts, like say sodium chloride, will be very, very different from those in, let's say, binary Lennard-Jones mixtures. That's really the case. So the long range interaction will promote so-called these waves of polarization, so these optic-like modes. They will have a long lifetime, and will be comparable, very, very comparable to the lifetime of hydrodynamic modes. However, they will be much higher in frequency. This is really, really very, very, very specific feature of systems with long range interaction. Yes, you are right.
Also, there are experiments, as I understand, for molten salts, for sodium chloride, as you mentioned. There are experiments about these systems.
Well, there are many experiments in elastic X-ray scattering. People, especially in Japan and in ESRF in Grenoble, they are performing lots of experiments, and they are very, very interesting in our analysis. In our analysis, both of liquids and gases. And right now we are collaborating with Japanese group, namely in this issue, how to find the contribution of non-ergodicity to the sound dispersion they performed already in elastic X-ray scattering experiments on selenium glass. Selenium is the only known stable glass of one component system. Because for others like argon and others, those glasses are not stable. But for selenium, it's quite stable glass of one component. And what we are doing now, we are together, actually, Ari Seitsonen is in Kyiv. So Ari Seitsonen is performing machine learning and ab initio simulations for this selenium glass. So, and yeah, there are many experiments for liquid systems, for glasses, not much on confined system, but for liquids there are a lot of experiments, and many people actually are interested in this explanation of positive sound dispersion, because namely from the experiments, the experimentalists observe this positive sound dispersion in liquids.
Thank you. Yaroslav,
okay, I have a question and a comment. Could you show the page with your one-dimensional channels? Yes, this one. Could you just clarify this graphs? What is along the x-axis? Is it the width of the channel?
Along X? No,
No,
the width of
up.
one-
In
one
the no,
1.5.
in the plots, up there along the x axis. What is no?
Well,
no,
along
no.
X.
Yes, in there. Is it the width?
The width is 1.5.
No, in your plots, what is the quantity which you have along the x-axis, because we don't see it, it's too small. See,
Well, this here
no,
is density is equal to 1.
no,
Linear density equal to 1. And here is higher than 1 density.
no, the one to the right. The plot where we have the dependence. Just
This is profile.
yes, like this, yeah.
1.14.
The question is, it is the function of what against what? Because I just don't.
This is density profile.
Yes, the function of
Density
what?
profile along direction y. Along this direction.
The density along direction y. Okay, thanks.
Yes.
And then the question is it maybe it looks like that it depends strongly on the radius of your these particles.
Of course, yes. But this radius is sigma. Sigma is taken as 1. So everything is in units of sigma.
So it looks like the dependence might have a fractal structure, like depending on the commensurability. When the ratio is kind of rational, then you have one situation, and when you just move a little bit and it is irrational, then it can change very, very strongly. Maybe I'm mistaken.
Yeah, it's different on ratio. Dimension this is units, it's
So it's like devil's staircase in some sense. Okay, but okay, thank you. Well, because I just know that in other systems like Aubry and Andre transition, you can have very similar structures. Yeah, but and just small comment. It is a kind of positive comment because
Okay.
maybe you know, but maybe not. But there is activity in this area with water-filled carbon nanotubes. So
Yes, I know.
yeah,
At our institute, there is a group which are simulating this water molecule in a single wall nanotube. Yes, we know this.
that is very important. Yeah, thank you very much.
Thank you.
Taras Mikhailovich, very general question. What you mean by non-hydrodynamics? This is discreteness of the system. I mean, discreteness of the particle. Yeah.
Yes, but
So interaction between discrete particle.
yes, it's discrete, but on large distances, it's like you are changing your zoom, and you look from the very large distance. You have the uniform, and you don't see the resolution of particles. So in that sense, when you go to wave number goes to 0 for very large systems, for very small wave numbers, you must recover the hydrodynamic shape of time correlation functions. That's the law.
Thank you. Larissa Bryk, have a comment.
Yeah, Taras Mikhailovich, Larissa, thank you so much for very interesting talk, lecture, and research talk. The short comment regarding your last part of the talk and the slide which we see the page. Many years ago, I guess it was end of 80s, at our institute, when the computer simulation, what was the beginning of the computer simulations, there was the paper by Ilyin, Makovsky, and Davidov, as far as I remember, about water in confined areas, in channels or canals. And they have shown that the propagation of the liquid along narrow canals becomes much bigger, faster, almost like superfluidity appears. As far as I remember, there were no analytical model, but the numerical simulations have shown the existence, appearance of the collective dynamics, collective modes, exactly what you stressed in your talk. So that's very interesting how this research develops.
Okay,
Yes,
thank
yes,
you. I
thank
didn't
you.
know. I didn't know about that paper. I will search about Ilin's papers. Okay, thank you.
I am not sure that it has been published as a paper, but I will look at the preprint and will send you the reference. So maybe.
Okay, thank you, thank
Thank
you.
you.
Would be interesting.
Some question, please. It's, thank you, Taras Mikhailovich, very interesting talk. So our greetings to Lviv and
Yeah, thank you very much.